Good morning, class. We are looking at Chapter 2 review, limits, covering from 2.1 to 2.8. Here's the second part covering 2.4, the precise definition. That means the precise definition of a limit. 2.5, continuity. 2.6, limits at infinity, also known as how we find horizontal asymptotes. So having said that, the precise definition, and I want to give you the synopsis of that concept down here. I read that for you, and then we look at more details. So what does this mean? Starting with a function, limit of f of x as x approaches 3 equals 5 means f of x is close to 5 when x is close to 3. So since x is approaching 3, in the vicinity of 3, we go to the left and right by a small number delta. Then the y coordinate is 5. In the vicinity of 5, go up and down by a little bit, a small number, epsilon. So whatever, this notation in math is whatever, epsilon larger than 0, there exists delta larger than 0, such that if the absolute value of x minus a is less than delta, the absolute value of f of x minus l is less than epsilon. I write this and then I erase them. So this reads whatever this means there exists, and this line segment such that. So those are mathematical symbols. So in short, if the difference between x and a in an absolute value sense is less than delta, so that's what it means. If a happened to be some number, for example, 3, a is any number. So you go to the right and left a little bit, then the absolute value of f of x minus l, the distance from the two is less than epsilon. So f of x is within the number, l happened to be 5 here, by a little bit. That is the concept. Now, we can make the values of f of x within an arbitrary distance of epsilon, again, a very small number from 5, by restricting the values of x to be within distance delta from 3, but x is not equal to 3. So we are close to 3, either from the left or right, and again, delta is a very small number. If you look at this absolute value, okay, x minus a, that means, reminding you, that means x minus a is between negative and positive delta. Now, if you move the a, you get this one. This is by the definition of an absolute value. So if x is between 3 minus delta and 3 plus delta, then f of x is between 5 minus epsilon and 5 plus epsilon. So x is some number between these two values, 3 minus delta, 3 plus delta, along the x-axis. Then f of x, or the y coordinate, is between 5 minus epsilon and 5 plus epsilon. By taking the values of x not equal to 3, and that's the idea. When it comes to limit, we are interested in the vicinity, not exactly what happens at that specific number, to lie in the interval of 3 minus delta and 3 plus delta. We can make the values of f of x lie in the interval of 5 minus epsilon and 5 plus epsilon. Precise definition of limits. Let f of x be a function defined on some open interval that contains ax, possibly at a itself. We say the function has a limit at a, the limit of f of x as x approaches a equals n. If for every small number epsilon larger than 0, there's a number delta larger than 0, again, both of them extremely small, such that if the absolute value of x minus a is between 0 and delta, that means is positive in essence, then the absolute value of f of x minus l is less than epsilon. In other words, this is how it maps. It maps somewhere in the interval of a minus delta and a plus delta. This is an interval along the x-axis to, it maps into L minus epsilon, L plus epsilon. That is the range. And that's the concept known as the limit. Bear in mind, again, I can't emphasize this enough. Delta and epsilon are extremely small numbers. Now, use the graph to find delta such that if absolute value of x minus 3 is between 0 and delta, absolute value of f of x minus 2 is less than 0.5. So here's, in essence, the limit of f of x as x approaches a is 3, and it's equal to L is 2. That's the concept. That's why we have the 2 here. So I'm going to write the general format that I mentioned. Whatever epsilon larger than 0, there exists delta larger than 0, such that if absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. So the idea is that guessing a value for delta given epsilon larger than 0, we need to find or guess delta positive such that if x minus a is the absolute value is between 0 and delta, then absolute value of f of x minus L is less than epsilon. So let's see what happens. First of all, as far as the graph is concerned, I hope you see that it basically means this distance and this distance from 3, this distance from 2, this distance from 2. As you can see from 2, the two distances are identical and they happen to be 0.5, as you can see. So that is fixed. But we, generally speaking, this is easy, we can go here and see the map. But generally speaking, we start with the absolute value of f of x minus L, less than epsilon. So if you look at this one, you're going to rewrite this one. So we get absolute value of f of x minus 2 less than 0.5. And you know how to take care of the absolute value. Again, I'm going to remind you, I just went over that. If absolute value of x is less than a and a is positive, x is sandwiched between the two values. Therefore, f of x minus 2 is between negative 0.5 and 0.5. And now you add the 2 to all sides, 2. And of course, you can see that from the graph. But just in case it's not given, you can easily come up with that. So that is not a big deal. Now, what about delta? Well, we start from 3 and we go to the left and right, and we see the numbers that are given to us are 2.6 and 3.8. So x is somewhere between 2.6 and 3.8. If x is somewhere there, that means if it's here, it's coming from the right of 3. If it's here, it comes from the left of 3. But the question is, what should delta be? Delta refers to this distance. So there are two distances that we are dealing with. One of them is 3 minus 2.6. One of them is 3.8 minus 3. One of them is this distance. One of them is this distance. You should always choose the smaller of the two. Take delta to be the minimum of this distance, 3 minus 2.6. This distance, 3.8 minus 3. The smaller of the two, which makes this 1.4, which makes this 1.8, and the answer is 0.4. Now, why the smaller? If you pick the smaller one, this one, okay. So worst case scenario on the left side we get here. On the right side, if you go with 0.4 instead of 0.8, you end up here. You end up here, and it still works. However, if you choose the bigger one, on the right side, you're fine. The bigger one is 0.8, and it gives you maximum to this. But what about the left side? If you go with the bigger one on this side, and this is 0.8, now this end point will give you somewhere that it's not within the indicated limit. So you must always, if the graph is given, calculate the two distances and pick the smaller the one. And of course, anything smaller than that works. So any smaller number than 0.4 will do. And of course, x can't be equal to 3. But if you choose any number larger than 0.4, on this side, we're going to have a problem. Now, prove that the limit of 4x minus 5 as x approaches 3 equals 7. Again, I'm reminding you, whatever epsilon larger than 0, there is delta larger than 0, such that if x minus a, the absolute value is less than delta, then the absolute value of f of x minus L must be less than epsilon. And of course, the idea is a guessing game. What do we come up with? Guessing a value for delta given epsilon larger than 0, we need to find or guess delta larger than 0 such that this will result in this. And so with that being the case, we are going to write this for a given limit. So everybody, we want to take the limit of 4x minus 5 as x approaches 3. So a is 3. And that's equal to 7. That means absolute value of f of x minus L. L is 7. F of x is 4x minus 5. According to this, a is 3. F of x is 4x minus 5. L is 7. So it's pretty straightforward, everybody. And we start with this. The absolute value of 4x minus 5 minus 7, that makes this one minus 5 minus 7 is minus 12, less than epsilon. So we always start with that. And we want to end up here. So the bottom line is we want to find the relationship between epsilon and delta. So notice, again, so we want to make this look like that. Notice we can take the 4 out. And the moment we take the 4 out, it becomes this. So we take the 4 also outside the absolute value because you can take a positive value out. The absolute value of 4 is 4. And now if I divide both sides by 4, this goes away. And absolute value of x minus 3 becomes less than epsilon over 4. So working with the limit, we wrote this piece, the second part here. And the second part ended up looking almost like the first part. So look at this one. We showed that this will result in absolute value of x minus 3 less than epsilon over 4 on the one hand. On the other hand, the absolute value of x minus 3 is less than delta. That is okay. So compare it to absolute value of x minus a less than delta and choose delta. So put it next to it. So if the left side is identical, so must be the right side. So the choice of delta must be epsilon over 4. And of course, that means even anything smaller than that will work. And for our practical purposes, you're done. But the proof is actually to reverse the process. Okay, that's how they do that. So showing that this delta works, reverse steps. So we are going to start with this, and this is equal to epsilon over 4, right? Epsilon over 4. That is the choice of delta. So what is delta? Epsilon over 4. If we multiply, remember, we want to come back to this, everybody. We want to get back to this. So the idea is to go back to what we started. So let's multiply both sides by 4. So you put the 4 here, and this becomes epsilon. I can take the 4 inside. I get 4x minus 12. And since I want to go back to this format, I'm going to rewrite this as 4x minus 5 minus 7. 4x minus 5 minus 7 looks exactly like that. So that means this resulted in that. So write those next to each other. And that means if the absolute value of x minus 3 is less than delta, that means the absolute value of 4x minus 5 minus 7 is less than epsilon. And therefore, the limit of 4x minus 5 as x approaches 3 equal to 7. Now, that is the methodology. And as far as the graph is concerned, take a look. Number 3, in the vicinity of 3, delta to the left and right, so 3 minus delta, 3 plus delta, results in the functional value of 7 within epsilon. So 7 minus epsilon and 7 plus epsilon. So it's very straightforward, everybody. All right. Continuity. A function has a limit at a if the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right, both of them are L. Therefore, the limit of f of x as x approaches a equals L. Direct substitution property. For polynomials or rational functions, if the function exists at the value of a, then the limit of the function as x approaches c is equal to the function's value at a, which means limit of f of x as x approaches a equals f of a. And that's the definition of a continuity. So a function is continuous if this limit that we have discussed, one-sided limits are identical, the limit exists, so the limit of f of x as x approaches a equals to f of a. This is the limit, this is the functional value. That means basically there's no hole or anything, any type of a discontinuity. Vertical asymptote, you name it. A function is continuous from the right if the limit of f of x as x approaches a from the right is f of a, and a function is continuous from the left if the limit of f of x as x approaches a from the left equals f of a. A function may be continuous on the left or right. We will have that discussed. And now, if you look at this one, it gives rise to what we are calling the intermediate value theorem, short IVT. If f of x is a continuous function, there's no break, there's no hole, on the closed interval of a to b, so we go from a to b, and the function is continuous. And let n be any number between f of a and f of b. So the endpoints f of a and f of b, they have some functional values f of a and f of b, and n, we choose it to be somewhere in between, where the two values are not equal. There must exist a number c in the interval of a to b such that f of c equals n. If this is a continuous function, this is the key, and f of a and f of b are different, and n is somewhere in between, the function must cross it at some point, and that means at least one point. there may be more. Normally, this is used to indicate that there is a zero, because normally we go with a value such that f of a and f of b have different signs. One is negative, one is positive. Therefore, zero is in between. All right. Determine C such that P of X is continuous at X equals 5, where P of X is defined as a piecewise defined function, X squared minus 25 over X minus 5, for X not equal to 5, and it will be C for X equals 5. So we have to look at two things, the limit and a functional value. So we take the limit as X approaches A, in this case, X equals 5. So let's take the P of X, limit of P of X as X approaches 5, which means we're going to look at this piece, because this function is always the case when X is not equal to 5. And that's exactly what we use for the limit. Notice we plug in 5, we get 0 over 0. The technique is factoring. Numerator is a squared minus b squared. So this is x squared minus 5 squared. So x minus 5x plus 5. Also remember, because x is approaching 5, makes the denominator 0, so we should have a factor of x minus 5, and we do. These two cancel each other. The limit of x plus 5 as x approaches 5, you plug in, you get. So the limit does exist, and it's equal to 10. The functional value at x equals 5 does exist, and P of 5 equals C. So it will be continuous if the two are the same. So the choice of C must be 10. Show the function is continuous and negative to positive infinity, f of x is sine x, if x is less than pi over 4 cosine x, if x is larger than or equal to pi over 4. We have a piecewise defined function. Each piece is a trigonometric function, sinusoidal functions. As you know, the domain for each one is all real numbers. So trig functions sine and cosine are continuous or negative to positive infinity. Therefore, this function is continuous as follows. F of x is continuous on the interval of negative infinity to pi over 4 union pi over 4 to infinity. We don't know about the endpoint. We should check it. So let's check the endpoint pi over 4. The limit of f of x as x approaches pi over 4 from the left uses the top piece, sine x. Plug in, as you know, sine of pi over 4 is square root of 2 over 2. Same thing, but from the right uses the bottom piece. So limit of f of x as x approaches pi over 4 from the right is the limit of the second piece, cosine x, as x approaches pi over 4 from the right, which makes it cosine of pi over 4. As you know, that is also square root of 2 over 2. So everybody should know basic trigonometric functions and their values. Okay, everybody? So the limit of f of x as x approaches pi over 4 is square root of 2 over 2 because one-sided limits are the same. Also, f of pi over 4, you use the equality, you use the second piece, and that is square root of 2 over 2. So pretty much everything is in order now. The limit of f of x as x approaches pi over 4 is the same as f of pi over 4, and it's equal to square root of 2 over 2. Therefore, it makes it continuous at pi over 4, and we already know that it's continuous everywhere. We are just looking for pi over 4. We prove that works. Therefore, it makes f continuous on the entire interval of negative to positive infinity. Types of discontinuities. Look at this function with a whole. F of x is x squared minus x minus 2 over x minus 2. Look at this function is the same thing with a whole. And then we have a piecewise defined function, and we define, in this case, as at x equals 2, we have no idea what it is. In this case, at x equals 2 as the y coordinate 1. So what are we looking at? Parts A and C are known as removable discontinuities. That means we can fix them. We could remove the discontinuity by redefining f of x at just the single number 2. In this case, you just redefine it and you fix it. And by the way, everybody remembers that you have a rational function. When you can factor and drop the denominator, the fact that x can't be equal to 2 remains. That creates a hole in a line. That's what happens here. So this is x minus 2x plus 1 over x minus 2. You drop the x minus 2, you get x plus 1. It's important to know it is the line y equals x plus 1 would be this line, but this function is the line and it has a hole. Okay. So x can't be 2. So if you plug in 2 here and it becomes 3, that means this point, by the way, has coordinates 2, and then 2 plus 1, 3. So if you redefine this, instead of 1, if you put 3, it fixes the problem. That's the idea. That's why it's called removable. It can be fixed. There's only one discontinuity. However, so the function g of x equals x plus 1 is continuous. Okay. This line is continuous. However, if you look at this one, okay, we have a vertical asymptote, and in this case, we have a jump. So part B, infinite discontinuity or vertical asymptote, there is no way to fix this. This one, jump discontinuities. There's no way to fix it. It jumps. So this is removable. The other ones are not. Here's the graph. At what point or points is the function f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? How would you fix it? So let's look at the discontinuities. And again, class, I'm reminding you of the definition of a one-sided limit. Okay. A function has a limit if the limit on the left and right are identical. That's really the bottom line, is pretty straightforward, everybody. Now, also, a function is continuous at x equals a if the limit and functional value are the same. Okay, so just knowing that. And now, what are the discontinuities? You see the discontinuity here at -2, at this point, -0.5, over here, 0, 1, 3, 5. So those are the points. Now we're going to discuss each one. So as you can see, at 0, it jumps from here to here. At 1, it jumps from here to there. So we have a jump at 0, at 1. This is what? Vertical asymptote. So number 3, VA or infinite or vertical asymptote. The rest of it, look at -2, you have a hole. Look at -0.5, you have a hole, negative, and +5, you have a hole. The rest of them, -2, -0.5, and 5, we call them removable discontinuities. How would you redefine to fix it? That's the idea. Starting with -2, there's a hole. So what is the y coordinate of that point? 2. So we're going to say f of -2 must be 2. So please understand, as you approach -2 from the left, you're in this branch. From the right, you're in this branch. In both cases, you're going towards this point. So the limit exists, and it's equal to 2. Therefore, because the limit of f of x as x approaches -2 exists and is equal to 2, then we define it as 2. F of -2, if we choose it to be 2, it fixes the problem. The next number is -0.5. Look at -0.5 here. So the left, here's -0.5 roughly. The left and right is going to take us here, which results in the limit to be at 3.5. Okay, so this is 3.5. And we say the limit of f of x as x approaches -0.5 is 3.5. So that's how we define it. F of -0.5 must be 3.5 to fix the problem, everybody. The last number is 5. So here's 5, left and right, left and right. So from the left, from the right, you're moving towards the same point, which seems to have a y coordinate of 5. So limit of f of x as x approaches 5 is 5, and therefore we choose f of 5 to be 5. That's how you fix the discontinuity in the case of a removable discontinuities. Use the intermediate value theorem to show there is a root for the equation sine x equals x squared minus x in the interval of 1, 2, 3. Reminding you, the intermediate value theorem, or IVT, indicates if f of x is continuous function on the closed interval of a to b, and let n be any number between the two values, f of a and f of b, where the two values are not equal, there must exist number c in ab such that f of c equals a. Now, Because we are looking to find there is a root, that means the left and right are equal, or that means if you bring them to the same side, you bring everything to the left or to the right, makes no difference. That is equal to 0. That means you want to find that the functional value in here somewhere is negative, somewhere is positive, okay? So we're going to call this f of x, and f of x is x squared minus x minus 6 is a continuous function. The reason it's continuous, because the combination of quadratic function and sinusoidal function, therefore it makes it a continuous function. So we are going to look at f of 1 and see what we get. If f of 1 is less than 0, let's see why. Plug in. I hope you see that this is 1. With this one cancel each other. Negative sine 1. 1 is 1 radian. It's about 57.3 degrees. You don't even have to know what it is to know that this is negative, everybody. This value minus sine 1 makes it negative. On the other hand, if we put 3, so this is negative sine 1. And negative sine 1 is negative. Now, if we put number 3, that's larger than 0. How do we know that? Well, just plug in. This is 9 minus 3 is 6. 6 minus sine 3. As you know, sine, the largest value is 1. So 6 minus that must be positive. And because 0 is somewhere between negative and positive, IVT, intermediate value theorem, applies. F of x is continuous on 1, 2, 3, the interval of 1, 2, 3, and has a root in between. So that's pretty straightforward, everybody. So in short, if you want to find a root, a 0 of a function, just you have to show somewhere in between the function is negative and somewhere is positive, and therefore 0 is in between, as long as the function is a continuous function in that given interval, everybody. Limits of functions at infinity. Here's the summary. We're going to define horizontal asymptotes short HA of the curve y equals f of x is y equals L, as long as limit of f of x as x approaches negative infinity is L, or limit of f of x as x approaches infinity is L. So negative infinity or positive infinity. Now, for example, the limit of 1 over x as x approaches infinity is 0. The limit of 1 over x to the power of p as x approaches infinity is 0. Granted, p must be larger than 0, because class, if p is negative, remember it comes up the negative exponential rules. So for example, we are familiar with exponential functions. This is an exponential growth if the base b is larger than 1. And so in this case, the b is between 0 and 1, and it makes it an exponential decay. So as you look at them, the limit of, for example, e to the power of x, the limit of e to the power of x as x approaches minus infinity is 0, and that makes the line y equals 0 for the x-axis, the horizontal asymptote. And of course, you see this one, the limit of f of x as x approaches infinity is the first quadrant. This one, the limit of f of x as x approaches negative infinity is infinity, the second quadrant, and the limit of, as an example, e to the power minus x. The limit of e to the power minus x as x approaches infinity is 0. And in both cases, you see the horizontal asymptote is the x-axis, and the x-axis has the equation y equals 0. Now, this concept is really known as the end behavior, as you probably remember from algebra. For example, in the case of a cube function, y equals x cubed, the limit of f of x as x approaches negative infinity is negative infinity, which refers to the third quadrant. And the limit of f of x as x approaches infinity is infinity, which refers to the first quadrant. Obviously, there's no asymptotes, known as the end behavior, everybody, known as the end behavior. Infinite limits, VA, vertical asymptotes. If the limit of f of x as x approaches a, or a from the left, or a from the right, is negative infinity or positive infinity, one of them, then the equation x equals a is the VA or vertical asymptote. You are familiar with the natural log, or in general logs when the base is larger than 1, looking like that with the x-intercept at 1, 0. As you can see, the limit, so the domain is 0 to infinity, and the limit of ln x as x approaches 0 from the right is negative infinity, which means the y-axis, which has the equation x equals 0, is the vertical asymptote, the y-axis. So definition, vertical asymptote of the curve y equals f of x is x equals a. If the limit of f of x as x approaches is plus minus infinity, one of them, or limit of f of x as x approaches a from the left is plus minus infinity, or from the right. So that's the definition of a VA. As you probably recognize, this is the tan x. And the limit of tan x as x approaches negative power 2 from the left is minus infinity, which makes x equals minus power 2 one of the vertical asymptotes. And the limit of tan x as x approaches power 2 from the right is infinity, which makes x equals power 2 another one, okay, in a complete cycle. And of course, as you know, tangent continues indefinitely on both sides. And that gives rise to horizontal asymptotes for its inverse. So here's the inverse tan. The limit of tan inverse of x as x approaches negative infinity is minus power 2. The limit of tan inverse of x as x approaches infinity power 2. Therefore, the horizontal asymptotes are y equals power 2 and y equals negative power 2 by definition. Find the limits, and we are going to find the limits in essence algebraically, everybody. I'm going to remind you that we plug in limit of f of x as x approaches a. Gives us a number is done, 0 over some number is 0 is done. A number over 0, just figure out positive or negative infinity. But in calculus, we end up with the last case almost always. So if you replace the t with infinity, I hope you recognize that this is infinity over infinity, one of those indeterminate forms. And then there's a technique. Now, when the variable approaches infinity and the expression is a rational expression, then you divide by highest degree term in the denominator, namely t squared. You simplify each piece, each term. This is 5 over t, this is 7 over t squared, this is 1, 2 over t minus 1 over t squared. So t is approaching infinity, which means 5 over a huge number, 7 over a huge number. In essence, if you plug in, everything goes to 0 except the 1. So you have 0 plus 0 over 1 plus 0 minus 0. I write it in this fashion because I want you to see 0 over 1, which is 0. So the denominator is some number other than 0. If we look at this case, it works out to be the same. And you get infinity over infinity. You divide by highest degree term in the denominator. This time it's t. So you divide everything by t. And we simplify. The limit of t plus 2 over 7 over t over 5 plus 7 over t as t approaches infinity. So this is infinity. This is 2. This is 0. This is 5. This is 0. So it's important to know the numerator is infinity, everybody. Infinity plus 2 times 2 minus 2 plus 1 billion minus 1 billion is infinity. Divided by 5 or 5,000 or 5 billion, it's still infinity. What can change it, if it happened to be negative, then the result is negative infinity. Okay? That you want to be careful of. All right. The limit of the square root of x squared plus 1 minus x as x approaches infinity. Now, if you plug in, this becomes infinity squared plus 1. The square root of that is infinity. So it's infinity minus infinity. What is the technique here? Conjugate. What is the conjugate? The conjugate of this expression, you write the same thing, but you change this to a plus sign. But you can't just multiply by that. You have to also divide by it. Why? Because you can't multiply by anything you want, but you can multiply by 1. This expression, because the top and the bottom are identical, equals 1, and you can do that. And we use the fact that a minus ba plus b is a squared minus b squared. So we use the conjugate, and we use the fact that a minus b times a plus b is a squared minus b squared. So what happens? Let's find out. When we want to multiply those two, let's extend this fraction bar. So the denominator is looking at us, x squared of x squared plus 1 plus x. But what is the numerator? The product of these two becomes, let me just write it down here, and I'm going to erase it. Square root of x squared plus 1 quantity squared minus x quantity squared. This is the numerator, everybody. So it comes out as x squared plus 1 minus x. Okay, so I used a minus ba plus b equals a squared minus b squared to get to the result. And now these two cancel each other. We get this one. Now, if you put the infinity, then the denominator is infinity plus infinity, which is still infinity, and it's 0. So it's important to know infinity minus infinity can be 0, can be infinity, can be a number in between, can be negative infinity. So which one? You have to work it out to figure it out. I can't emphasize this enough, everybody. We want to find the limit of 12 over 4 plus 3 to the power minus t as t approaches infinity. So basically you plug in and it becomes e to the power of minus infinity, which is 0. Why is that? Negative exponential rule indicates a to the power of minus m is 1 over a to the power of m. Therefore, e to the power of minus t is 1 over e to the power of t, right? So this one is 1 over e to the power of t. So 1 over e to the power of infinity, which is 1 over infinity, which is 0. That's what happens, and the answer is 3. What about this case? I hope you realize if we plug in, this goes to infinity and this goes to infinity, with the negative makes it negative infinity. Infinity over negative infinity is indeterminate. This is not a rational expression because the top and the bottom must be polynomials to be rational expression. E to the power of t is known as a transcendental function, but nevertheless, it's a fractional format. When t is approaching infinity, the technique is to divide by highest value in the denominator, which is e to the power of t. So divide everything by e to the power of t and simplify. So this simplifies to 1, this simplifies to -3. And now if you apply t approaching infinity, this goes to 0, this goes to 0, and we get 1 over -3, which is -1/3. The limit of x squared minus x as x approaches infinity, it is also infinity minus infinity because x squared, remember, infinity to the second power or even square root of infinity is still infinity. So what is the technique? The technique is factoring. We can take the x out. Now, if we plug in, we get infinity times infinity minus 1, which is again infinity. So indeterminate form of infinity minus infinity could be any number. Limit of x squared plus x over 3 minus x as x approaches infinity. Again, you have a rational expression. Because x is approaching infinity, you divide by highest degree term in the denominator, namely x, and simplify. You plug in, the numerator becomes infinity plus 1, which is infinity. The denominator is 0 minus 1. So I want you to be careful. The answer is negative infinity because you're dividing positive over negative. Okay. The limit of e to the power minus x plus 2 cosine 3x as x approaches infinity, we first cut it into 2 pieces. Limit of this piece plus 2 times the limit of this piece. And this doesn't exist. Why is that? First and foremost, everybody, this you plug in goes to 0. So that's fine. 0 plus 1. Now this piece, D and E, does not exist because generally speaking, the limit of cosine ax as x approaches infinity, the limit of sine ax as x approaches infinity does not exist because they oscillate between -1 and 1. As you know, the range for sine and cosine is -1 and 1, so they oscillate between the two values. They don't settle down, and this creates a problem. This is fine. This creates a problem. Therefore, it does not exist. What about the limit of e to the power of 3x minus e to the power minus 3x over e to the power of 3x plus e to the power minus 3x? Again, this is not a rational function. However, it's a fractional format where x is approaching infinity. You divide by highest degree term in the denominator. Please understand, if we plug in, we do get infinity over infinity. Okay? Because e to the power of 3 times infinity. This is infinity, this is infinity, this is 0, this is 0. Okay? So you divide by highest value in the denominator, which is e to the power of x. Let's divide everything by e to the power of 3x. Well, I want to remind you of a couple of things. Number one, a to the power of minus m is 1 over a to the power of m. That's why they become 0. Number two, a to the power of m over a to the power of m. N is a to the power of m minus n, known as the quotient rule. Okay. So you divide this one by this one, you get this. You divide this one by this one, you get e to the power minus 6x. So in case I want to show you, this is what happens for this piece, for example. E to the power of negative 3x over e to the power of 3x is e to the power of negative 3x minus 3x. That's how you get that. And of course, this e to the power minus 6 times infinity, that goes to 0. This goes to 0, so the answer is 1. The limit of tan inverse of ln x as x approaches 0 from the right. So you're taking the limit and it pertains to x, therefore it pertains to ln x. You can take the tan inverse out. So it says tan inverse of limit of ln x as x approaches 0 from the right. Now, we're going to concentrate on this, see what this becomes. You should know this is negative infinity because you should know the graph. If you look at the graph, and again, we've discussed that already. Okay, so as x approaches 0 from the right, it goes down. That's the concept of a vertical asymptote. So it goes down to negative infinity. So this is negative infinity. Tan inverse of negative infinity, if you go with the graph that this was a tangent, one complete cycle. Remember the vertical asymptote, x equals minus power 2 and power 2. And the inverse, those are the horizontal asymptotes. And therefore, for that, you can get negative power 2. One way to look at that, by the way, would be to use the following methodology. This means, okay, so what is this? So you are going to write tan of minus infinity. What is that? Let's call it alpha. By definition of an inverse function, tan of alpha must be negative infinity. And therefore, alpha, you should know it's one of the common arcs, is negative power 2. Okay, everybody, you can go that route as well using trigonometry, inverse trigonometric functions. Limit of sine squared x over x squared plus 1 as x approaches infinity. What is the technique? Let me erase my work so we can use the space here. Remember when we used the squeeze theorem and the technique that was discussed in the case of a squeeze theorem, whenever sinusoidal functions, sine, cosine, and so forth are involved, the technique or the trick is to start with sine. You know sine is between -1 and 1. So now we want to get this expression, everybody. We want to get this expression. To get this expression, we start with the numerator. That means let's raise it to the power of 2. If I raise this to the power of 2, I get sine squared. I get 1 squared root of 1. Remember, again, this you can't say it's 1 squared root of 1. You have to go with 0. I've discussed that. You can look at that recording if you want. So far we got the numerator. How do we get the denominator? So multiply by 1 over x squared plus 1. And because this expression is positive, and how do you know it's positive? X is approaching infinity. Because this expression is positive, the sign doesn't change. So let's multiply this side, doesn't change. This side becomes the expression we want, and this side is 1 over x squared plus 1. So using the squared the squeeze theorem. We take the limit of this one, obviously 0. We take the limit of this side as x approaches infinity, obviously 0. So 1 over x squared plus 1, x goes to infinity, 1 over infinity is 0. Therefore, the middle piece by the squeeze theorem, also known as the sandwich theorem, the limit of sine squared x over x squared plus 1 as x approaches infinity must be 0 by the squeeze theorem. You must mention the theorem, everybody. F of x is 2x squared plus 1 over 3x squared plus 2x minus 1. We want to find the asymptotes. Horizontal asymptotes, you have to take the limit as x approaches plus minus infinity. I'm going to discuss it from the point of view of pre-calculus in a moment. Okay. Remember, limit of f of x as x approaches positive or negative is L, then that becomes a horizontal asymptote, and VA, if the limit as x approaches A or from the left or right of A is negative or positive infinity. So we should know as far as the theorem is concerned. So how do you find this? Because x approaching infinity or negative infinity makes no difference, and this is a rational expression, the methodology is to divide by highest degree term in the denominator. So when we do that and we simplify, as you can see, everybody, this one, and this one goes to 0, we get 2/3, and therefore the horizontal asymptote has the equation y equals 2/3. Now, what I want to remind you before we go to the vertical asymptote, you recall in pre-calculus, when you have a rational expression, if the degree of the numerator is less, let me just write this. So you have f of x equals a sub n x to the power of n, and the denominator is b sub m x to the power of m, and you continue, right? Now, if n is less than m, then y equal to 0 is the horizontal asymptote. If n is equal to m, as it is the case here, both of them have degree 2, then y equals a sub n over b sub m. The coefficients take over. If n equals m plus 1, then we have oblique or slant asymptote. And that means you have to divide. This becomes mx plus b plus the remainder over the denominator. This y equals mx plus b becomes your oblique asymptote. I hope everybody remembers that. But the proper methodology is to divide, is to take the limit as x approaches positive, negative, infinity, and prove that horizontal asymptote is 2/3. For the vertical asymptote, for this to work, in order for the function go to positive or negative infinity, that means the denominator has to go to 0. It's important to know this indicates the denominator must go to 0. You set the denominator equal to 0. So let me erase this. And 3 is a prime number, 1 and 3, and this is just 1 and negative 1 in some order. When you do the factoring class, it's important to check the middle term. If you look at this one, minus x, this one 3x, they must add up to 2x, they do. So x equals 1/3, x equals negative 1. Those are the answers. Now we want to find a formula for a function that has a VA, vertical asymptote, x equals 1, x equals 3, horizontal asymptote, y equals 1. So let's see how we do that. Well, this is one possibility that we are going to discuss. We have f of x equals a fraction, a bar, and this is in the denominator. X equals 1 means x minus 1 is in the denominator. That's the meaning of this one. X equals 3, that means x minus 3 is in the denominator. Horizontal asymptote equals 1. If you look at the denominator, we have, let's see, we have x squared and the rest is not important. If you want y to be 1, the numerator has to be 1x squared. You can add anything you want. For example, I can add plus 2x, doesn't change anything, or minus 5, 2x minus 5, it still works. But the answer is this is one of the possible solutions, everybody. And that's the key. One of the possible solutions is x squared over x minus 1 times x minus 3.